amplifier design. In order for the amplifier to properly operate, so the gamma S and gamma L should be in a stable region. So here we have two types of stability. One is called the unconditionally stability, and the other one is conditionally stability. Unconditionally stability means that the gamma S or gamma L is stable, while conditionally stability means it has some condition for the gamma S and gamma L to be stable. So for the unconditional stability, gamma in should be less than 1 and gamma out for less than 1 for all passive source and load impedance. That means gamma S and gamma L should be less than 1. For the conditionally stable, okay, beside gamma in and gamma out should be less than 1. Gamma in and gamma out should follow this formula. So gamma in S11 plus S12 S21 gamma L divided by 1 minus S22 gamma L, which is less than 1, and so on for the gamma out. So stability circles defined as the low C in the gamma L and gamma S plane for which gamma in equivalent to 1 or gamma out is equivalent 1. So basically, the output stability circles, so beside on the Smith chart, we need to determine the output and input stability circle. So output for the load, input for the source. The stability circle can be drawn which near to the Smith chart by determining the center of the stability circle and the radius of the stability circle. So this can be determined by calculating using this formula. Okay, for CL and RL, C means the center of the stability circle, while R is the radius of the stability circle, and so on for the input and output. While delta can be calculated between all the S parameters. So basically, okay. So later so this is the Smith chart. So from the Smith chart, we can draw additional stability circle. For example, here is the stability circle, which has the distance is CL at the angle of, for example, at 37 degree. This is just example, okay, with the radius of, so this is the radius of RL, okay, of the stability circle. So this is just example on the Smith chart where we can draw the stability circle. So we want to determine whether it is unconditionally stable or conditionally stable for the design of the amplifier. If the device is unconditionally stable, okay, the stability circles must be completely outside of the Smith chart. So we can state that this result as CL minus RL, which is more than 1 for S11 equivalent to 1, CS minus RS for more than 1 for S22, which is less than 1. For the case of S11 and S22 is more than 1, the amplifier cannot be unconditionally stable. So alternatively, it can be shown that amplifier will be unconditionally stable if these conditions are met. So we need to determine whether it is conditionally stable or unconditionally stable, and where is the region of stability and not stable. So we look at this example. Okay, so this is the example that I have conclude based on the equation just now. So unconditionally stable. So that's mean no conditional, no condition for the amplifier to be stable. So this case happen for the case of S11 is equivalent to 1 for the case, for this case. So that's mean that the stability circle is completely outside of the Smith chart. So you can choose any value in the Smith chart. Okay, let's say I choose here. So which is gamma in will be less than 1. So everything is inside the Smith chart is less than 1. Okay, so the amplifier can operate properly within this area. So this for the case of the input, and for the case of output, the S22 must be less than 1. So here for the input, S11 must less than 1. And here also, the stability circle that you draw just now, which is you have the CL and with the RL of radius, which is completely outside of the Smith chart. For the case of conditionally stable, okay, so here we look at the case that CLRL, so center of the stability circle minus the RL is less than 1. And for the case of S11, which is less than 1. For the case of, for this case, so you can see that normally the Smith chart will intercept with the stability circle. So here the stability circle, let's say here, so CL, so I guess CL will be more than 1, and RL maybe less than 1 or more also can. Okay, so you will have some interception here. So here you need to choose whether the gamma in is outside of the stability circle or not. So here for the case of S11 less than 1, the stability region or the stability region is this area where the shaded form. So I should change the color. Okay, so the shaded form is the area where the amplifier will operate properly at that frequency. So here you can choose any value of gamma in inside the Smith chart. For the case of S11, which is more than 1, okay, so the stability region only appear at this region. Okay, so if you choose here, so it is not stable. But if you choose here, so it will be a stable region. So in determining for the amplifier design, so you must make sure that your chosen gamma in should be in the stability region. Okay. Besides drawing or calculation, we have another methods in order to determine the whether it is unconditionally stable or conditionally stable. So one of it is to use the K delta. So what is K delta? We need to calculate the K value and delta value. If K is more than 1, based on this equation, okay, and delta is less than 1, so it will be unconditionally stability. If you get K is less than 1, and delta still less than 1, so it is conditionally stability. So that's the first method of calculation. Second method of calculation is to use the mu value. So mu value here, okay, so you need to determine the S11, conjugate S11 is to 2, and based on the S parameters only. And if mu is more than 1, so it will be in the it will be unconditionally stable. So you need to make sure what is unconditionally stable and what is conditionally stable. Example here, okay. Ganham T has the following scattering parameters at 1.9 GHz, Z0 50 ohm. So given all the S parameters, S12 here is not 0, although the value is small, but it is not 0. So determine the stability of the transistor by using the K delta and the mu test and plot the stability circle on a Smith chart. So here, okay, so you can use the K delta or the mu test. Here, delta is equivalent to 0.336 and 0.383. So what happened here? Does it meet the requirement? Okay, let's see. So K is less than 1. So it's not meeting the requirement. Is it? Okay. Delta is less than 1. So it is conditionally stability. So this is a case for the conditionally stability. So that means there's possibility that the stability circle will intercept with the Smith chart. Okay, and you need to look in this case for the S11 value. So whether the S11 value is less than 1 or more than 1. So in this case, S11 is less than 1. So we expect that the area where the stability could happen is inside the Smith chart. So this where we can choose the gamma in. Gamma S and gamma L. Okay, you can choose gamma S or gamma L within the this area. Gamma S for input, gamma L for output. So in order to draw the stability circle, so you need to have to calculate all the CL, RL, CS, and RS. Here, so you will have 1.59, 132 degree with radius of 0.195 and so on. So here S11 is and S22 is less than 1. So the central part of the Smith chart represent the stable region where we can choose the gamma S and gamma L. Okay. Okay, here, how do you want to draw on the Smith chart? So let's say we took this value, 1.59, 120, 32. 1.59, 132. Okay. So before we proceed with that, so let's say you have this Smith chart. Okay. And you have print maybe on an A4 paper, A5 paper, and so on. Okay. The first thing you need to do is you take a ruler and you measure this distance. Okay. So let's say you take the ruler and you measure the distance and you find out that the distance is 0 or is 9 centimeter. The measurement is 9 centimeter. Okay, so next you determine the CL. The CL is 1.59 with a degree of 132 degree. Okay, so now on this Smith chart, so you need to determine the real value of the CL. So CL, the new one is 1.59 times 9 cm. Okay, here maybe you can get the 1.59, 1.6 approximately 9 cm. So 1.44 cm, 14.4 cm. So you take a ruler and you mark it as 132 degree. Where's 132 degree? So it is here. Okay, 132 degree. You take a ruler and you measure up to 14.4 cm. Let's say this is the 14.4 cm. This is just example. Okay. Okay. I think 14 should be higher. Okay. And then you take the next value of RL, which is 0.915. So this time you need to multiply with 0.915 times 9 centimeter. So you will get approximately 8.1 centimeter. So you measure it from here to here. The center of the stability circle. And the radius of the stability circle is 8 centimeter. So you measure here. You take the ruler and then you take the compass and you mark it. So here, so just I shaded here. So this is the region where unstable. And the other area is, this area is the stable region. And you need to do for both the load and the source. Okay, so this is the real results for the for this question. Okay, so actually you need to try it at home after this. So you can do it for both output stability circle and input stability circle. So your gamma S and gamma L value that you will choose should be within the Smith chart, which is the area for the stability happen. So this they call the stable region. What happens if you choose your gamma S and gamma L inside this unstable region? If you choose that, the amplifier will not work properly. Okay, so that's all for this section on stability circle, and we'll proceed with the amplifier design.